Elements of electrochemical machining process. The elements of the process are cathode tool of a shape which is almost the mirror image of the cavity to be machined into the workpiece, anode workpiece and means to hold and locate it near the tool, source of DC power of sufficient capacity so that high current densities can be maintained between the tool and workpiece, electrolyte, a conductive liquid and means to supply it into the gap between the tool and workpiece, tool work gap, cathode tool, the materials that find wide applications in the manufacture of tools for ECM are aluminium, brass, bronze, copper, carbon, stainless steel, monel, and reinforced plastics. Tools must be made undersized to adjust for overcut, which varies depending on electrolyte flow and required accuracy. Tool surfaces should be polished to a smooth finish, and a slight defect in the tool may affect the machining. Anode workpiece. There is no restriction on the nature of the work material except it must be a good conductor of electricity. The chemical characteristics of the work material, however, to affect the material removal rate. The removal rate is proportional to the atomic weight and inverse of the valency of work material. DC power and control system. A simple circuit is used in which the work is connected to the positive terminal of a DC supply and the tool connected to the negative terminal. The DC supply must be low voltage 2 to 20 volts but very high current up to 10,000 amps 100 amps per square centimeter. Electrolyte. The electrolyte used in ECM performs many functions such as completing the electric circuit between the tool and the workpiece, allowing desirable machining reactions to occur, carrying away heat generated during the chemical reactions, carrying away products of reaction from the zone of machining. An effective and efficient electrolyte should have the following characteristics: high electrical conductivity, low viscosity and high specific heat, chemical stability, resistance to formation of passivating film on work surface, non-corrosive and non-toxic in nature, inexpensive and readily available. Electrolyte can be divided into two classes: those composed of inorganic salts that produce insoluble byproducts known as sludging electrolytes, and those composed of acids or alkalis that result in byproducts that go into a solution known as non-sludging electrolyte. Sodium chloride, potassium chloride, sodium nitrate and sodium chlorate are some of the inorganic salts used in sludging electrolytes. Sodium chloride is the most commonly used electrolyte because of low cost and because its conductivity is stable over a broad pH range. However, sodium chloride is also very corrosive, produces a large amount of sludge and cannot be used on tungsten carbide or molybdenum, while non-sliding electrolytes such as sulfuric acid or sodium hydroxide do not produce the large amounts of sludge that the inorganic salts do. For certain specific materials, the non-sludging electrolytes produce the best results. Tool work gap. The gap can therefore be adjusted by voltage and tool feed rate. Under equilibrium conditions, the tool feed rate is directly proportional to current density. If the feed rate is increased, the electrical resistance of the gap reduces to allow more current to flow.